Hello, my name is Holden Bennett, and I'm presenting on elemental particles, which I have nicknamed atom.zip. So we're going to start off with the tree of elemental particles so that everyone understands pretty much what I'm going to be talking about for the rest of the time. So let's just start with this simple.zip folder, atom.zip, and let's extract that. Windows always makes me extract it using this stupid place called CERN. Ugh. Okay, now that we have our everything folder, we're going to open it, and as you can see, we have two folders inside of it, energy and matter. Let's start off by going down the energy trail. But before we do that, I need to tell you about two different principles that govern a lot about elemental particles that you need to understand before we continue. So the first is spin, and this is pretty much how we detect different types of particles. So say one particle spins at that speed while another spins at that speed. Those would be two different particles, and these spins are universal to that type of particle. Now the second thing we need to know about is called, and I'm just going to nickname it anti. And what this is like every particle has an opposite version of itself, but it's not opposite, it's anti, so it cancels the other out. This is very important for many different types of things involving the formation of protons and neutrons, but for the time being, we're just going to ignore it as it would have made this family tree of particles a lot longer and a lot more complex, and needlessly complex is the important part. So now we can get back to this energy folder. Now under energy, we pretty much have two other folders, bosons and leptons. Let's focus on bosons as they are some of my favorite particles in this entire tree. So there are three types. We have W and Z bosons, we have gluons and photons. And there are a couple more that we'll talk about later, but for the time being, let's just talk about these three, arguably four. So these are force particles, and let's just start off with W and Z bosons. These things are dubbed the weak force, so they govern this thing called the weak force. Oh, get out of here, Darth Vader. You're good enough for some people. So they play a role in particle decay, and this is what's really important. They play a role in how particles will decay into other particles. This is really important for a lot of stuff that has to do with say stars formation and any sort of nuclear reacting of any sorts. Now the next particle we're going to be talking about are gluons. These things are known as the strong force. They carry this thing called the strong force. Oh, yes, that's more like it. Sure, whatever. Anyway, so it is the glue that holds parts of protons and neutrons together, and this is really important for just in general stuff, which I think we can all agree is a very important part of life. Now, there is one more part to these gluons that has to do with Einstein's E equals mc squared famous equation, and we'll talk about that a little bit later, but for the time being, just know that they're very important to the formation of stuff. And these particles are also my favorite personally, just because of what they can do, and we'll talk about that a little later. Now, the next one I want to talk about is photons. Photons, as we know, are kind of like these light-emitting particles, and they're known as part of the electromagnetic force. That's why they are considered bosons, because they are like force-carrying particles. Also, they are both a ray and also a wave, and that's why they are signified by this symbol, because it starts as a wave and ends with a ray. And the reason we know this actually is a really interesting and famous experiment called the double slit experiment, where a bunch of photons were shot at two slits, and depending on with either they were rays or waves, they would have done different things, but for some reason they did the same thing, so we've kind of come to the conclusion that they are both rays and waves. Now, here's one of those interesting ones that we haven't really talked about. It's like this gravity boson that we don't really know if it exists. Theoretically, it should exist, just we have not actually found it. But it should theoretically exist. So now we're going to talk about leptons, which are also technically this group of things called fermions, but we don't need to worry about that because it gets confusing if we try and link that in. So these leptons, they have two groups inside them. We have neutrinos and electrons-ish, with like a huge asterisk. Let's just go into these electrons so I can show you what I mean. So we have the basic electron, the thing that floats around the outside of an atom. Those things are just signified with a little e. They're just the basic electron. But then we have these two, the tau and the muon. The tau, so these are the oddballs, right? The tau also has a negative charge, just like the electron. And the muon has a positive charge, so it's kind of like the opposite of the electron, but not the anti. You have to remember that. Now, the tau is interesting because it's actually 3,477 times heavier than the electron, which is an interesting little factoid. That's really what makes it different from the electron. Okay, so back under leptons, let's now go into neutrinos, which I like to signify with this little V8 bottle because it's anything that's a neutrino starts with a V and then the letter. So, for example, the E in the electron would be a VE. I'll just show you here. So you can see these V's. I find that fun. So these all look the same as before, except for none of these have charge, which is really interesting. They don't have charge, so they're just like the exact same particles, except for with the electron is no longer a negative particle, the tau is no longer a negative particle, the muon is no longer a positive particle. You just have to remember that when you think of neutrinos. Now, let's go back to this start of the tree, the everything tree. And this time let's go down the matter path, which is always a fun thing to do because you need matter to survive. So we really only have one folder under matter. It's protons and neutrons, and under that, we only really have one that we're going to talk about right now, and then there's the E equals mc squared one that I'm just going to say we'll talk about later. So we have quarks and stuff. And so let's talk about these quarks and stuffs. So quarks have many flavors, as they like to be called. And the quarks are also sometimes have inherent opposites that aren't their anti-variety. And you have to make this distinction because I'm about to show you what I mean. So we have up quarks and down quarks. So these are like the opposites. We have up, which is the opposite of down. But these also have the anti-up quark and the anti-down quark. So there are just two different types of things going on there. And that's the same situation for the top quark and the bottom quark. And then we have these two, which only actually have the anti-variety, not opposites. So we have strange quark and charm quark. But how does this relate to protons and neutrons? So the strong force, let's get back to this. This is created with gluons, and this is really what holds together these protons and neutrons. And it does this using these things called flux tubes. These things are pretty much vacuums within this web of gluons. So the proton is actually created with two up quarks and one down quark. This is where those quarks come into handy. And the neutron is kind of the opposite. It's two down quarks and one up quark. And that's the neutron. The way I like to think of it actually is the up and the down quark cancel each other out, and then there's one up quark left, and this is for the proton, but there's one up quark left, meaning that it has a positive charge, and on the two down quarks, it has one down quark left after it cancels out, and that last down quark is meaning that it's a neutral charge. Okay, so this is where I'm going to try to explain it with pictures. So we have this web of gluons, and floating around we have these two up quarks and a down quark. This is just for the protons, just for example. And they're connected with these flux tubes. These flux tubes are like vacuums, but you have to keep in mind that these vacuums are very difficult to pull. They require a lot of energy. So you have this kind of Y shape connecting all three of these. But here's the interesting part, and this is like the stereotypical proton. Now let's talk about how protons really look in the wild. Oftentimes, this is the rarity. Most of the time, they actually contain, so they have these flux tubes, right? But most of the time, they actually contain another type of quark mixed in. So like, say, a strange quark. They have a strange quark, but this can only exist if this strange quark has its anti-strange quark pair. And you might notice that these are actually not connected, but because they are in this same little bubble of flux tubes, it's still considered part of the proton. And this is also the same with the neutron. It's just instead of two up quarks, it's two down quarks. And let's talk about these gluons and these flux tubes, because these are really interesting, because they actually have a lot of weight. This is where most of your weight comes from. And this is also where we get this little E equals mc squared equation talking. So we have Einstein's famous equation, E equals mc squared. But what does that really mean? Well, what it means is we can get a lot of energy from just a little bit of mass. But if we flip this equation around, so it's m equals E over c squared, we can say that with a lot of energy, we can actually just create a little bit of mass. And what's lucky for us is that flux tubes require a lot of energy. So inherently, they also have a lot of mass. So what this means is most of your actual mass, because you have so many flux tubes, is actually coming from these flux tubes, this mass. So you have to think of it as energy is like almost interchangeable with mass. That's what you need to think about with this. But then there's this thing called the Higgs boson, and this is another one of those bosons from previously. It was discovered at this place called CERN, which is a giant collider, which collides two atoms, like particles, and we see what happens. And this thing is the Higgs boson, and it's often actually credited for like with mass. It's often credited for the existence of mass in general, which we just explained. A lot of things, most of your mass is actually coming from these flux tubes, but many people will say it's coming from this Higgs boson thing. This Higgs boson, though, is actually responsible for all the mass in electrons, but not protons and neutron pairs. So that's why I'm going to put these asterisks there, because that has a lot of asterisks there. So let's just explain this a little bit. So we got like a particle here, just floating in space, and we have this thing called the Higgs field. Let's think of it like an atmosphere. Now, when this electron is moving around, this atmosphere is pushing on it. It's pushing really hard, which makes this electron actually have this kind of weight. And that's what we're talking about when we say the Higgs boson is creating this kind of weight. And we just remember that these flux tubes are actually what's doing a lot of that work. And here's all my sources. We got a lot of sources. Switch between these pages if you need them. Okay, thank you for listening. Yeah, and if you need any other information, I can send you a link to a Google Doc, which has links to other sources that I have used in this presentation. Thank you.